It's wonderful to be here again in this beautiful place, and I apologize for actually arriving later, but I'm still in the semester and have some teaching duties, so I came as early as possible since yesterday was still teaching in the morning and had to catch my flight in the afternoon. Okay, so probably this is totally, the next slide is totally useless for this audience, but nonetheless, we have to write down the equations of interest at least once. So I'm going to talk about some theorems about the incompressible Euler equations that you see written over here. So as you see, the first equation is a vector-valued equation in the velocity of a fluid, which is assumed to be incompressible and ideal, so there is no friction between nearby fluid particles. So this is the balance of momentum, and as you see, the time derivative of the velocity is equal to this nonlinear term in blue plus the gradient of the pressure. And then the fluid is supposed to be incompressible, which means that the divergence of the vector field is equal to 0. Okay, so actually the blue term is the advective derivative of the velocity. So the ith component of this vector over here is just the sum over the spatial derivatives of the, so the sum over the spatial derivatives in direction xj of vj vi. So since actually v is divergence free, of course you can write this term if you have a smooth function also in this way. And this is probably more common in the literature. So usually the term is then written, the advective term is written in the following way. Okay, so in this talk I'm going actually to consider solutions over some time interval. Most of the times they are periodic solutions, so we're assuming that they are defined on the periodic torus. And of course the dimensions of interest for the space are the 3-dimensional space and the 2-dimensional space. Now, occasionally I will also actually assume that the space domain is the entire 3-dimensional space or the entire 2-dimensional space, but without assuming periodicity of the solution. I will warn you when that is happening. So if nothing is written down, then I'm assuming actually that the solution is periodic. The interval might be either a bounded interval or a half line. In this case, I will always assume that the left endpoint is 0. And of course, you assume the equations are complemented with some initial data at time 0. And this is the classical Cauchy problem for the incompressible Euler. Otherwise, sometimes I will assume actually that the time interval is the whole real line, and then I will use the name ancient solutions. So solutions which existed for all times back in the past and which exist for all times in the future. Okay, so the first thing that we are going to do is a very simple exercise in calculus. So if you have a pair V and P, which is a C1 solution, you can actually scalar multiply the first equation by V, and you can derive an interesting additional identity. This interesting additional identity is nothing but the balance of the energy. So it's nothing but the evolution of the kinetic energy. Okay, so you see what happens if I scalar multiply. The first term is Vj dt Vj. So here you see what happens when I scalar multiply the advective term, and then here there is just the scalar product between the V and the gradient of the pressure. So you recognize immediately that this thing over here is the time derivative of the modulus of V squared divided by 2. So it's just the time derivative of the kinetic energy density. Now, in here, of course, you can do the same. Since you have Vj times the derivative of Vj, you can sum over J first and write this as the derivative of modulus of V squared divided by 2. And then you see that you have the usual advective term. So this portion over here is nothing but this expression there. And then, of course, the last one is just V dot grad pressure. Now, since V is divergence free, you can rewrite this term as the divergence of what is in here times the velocity V. So now you have this blue term, which is just a divergence. So we are in the periodic setting. As I said, if I'm not telling you anything, we are in the periodic setting. So if I now integrate in the space variable, so on this side I get the time integral of the total kinetic energy. So here there's a 2 missing, but it's in the end not important because the result is equal to 0. And then when you integrate, of course, the term, which is a divergence, you integrate by parts, and that's equal to 0. So what you derive over here is nothing surprising. It's just the total conservation of the conservation of the total kinetic energy for smooth solutions of these equations, which is what you expect, because there is no viscosity to dissipate the total kinetic energy, and I'm not assuming the action of any external force on the field. So for a decent solution, of course, the total kinetic energy has to be preserved. Okay, so now let me switch to solutions which are less regular. So of course, the point here in this computation is that I'm assuming that the solution is C1, otherwise all these manipulations would just be formal, and they wouldn't be justified. So what happens if I have a weaker notion of solution? So first of all, what do I mean by a weak solution of the Euler equation? So there are a few ways in which you can actually define a weak solution to the Euler equations. They are all meaningful, and they all have some interest, and also they all happen actually to give the same concept. So one first thing that you can do is you could just say, okay, so the only nonlinear term is v tensor v. If I have the velocity which is square summable, I can certainly make sense of this matrix v tensor v, whose entries are just the products of components of the velocity, and they would just be L1 functions. So in the sense of distribution, I can define v tensor v once actually v is square summable. And then, of course, in the equation, in the way I've written, the derivatives are all taken after the nonlinearity, right? So I can actually define all derivatives in the sense of distributions. And then I can say, okay, a solution Vp in the sense of distribution is just an L2 function V and a distribution pressure P, which solve the equations in the sense of distributions once I have defined V tensor V in the usual way as product of functions. That's one possibility. There is another possibility. So what you could do, of course, what actually it's done often in the literature, since you are studying the incompressible Euler equations in a periodic setting, for each fixed time, you could write your your velocity v and your pressure p in Fourier series. Once you write actually in Fourier series, your evolution equation, which was a PDE, becomes an infinite system of ordinary differential equations for the Fourier coefficients. Of course, you might wonder when you do such computations, what happens to this nonlinear term over here, right? I mean, as long as I look at these terms over here, I will just have essentially one frequency popping out in the Fourier expansion of this expression. But of course, when I'm going to have a nonlinearity, I will have a series which is involving all the Fourier coefficients. So you might ask, I'm not going to do the computation, under which assumptions can I define actually this series? So under which assumptions this series is summable? And it turns out that it's precisely the same assumptions that you have over here. So the series that you get is summable if the velocity is in L2. Of course, if you're writing this for every single time t, then maybe a more natural assumption is to assume that the velocity is in L2. So the space trace of the velocity is in L2 for every time t that you pick up. Okay, there's actually a third way, which is interesting, because I mean, one could advocate that the third point actually comes even before you write down the equations in the classical way. And this is just to take the point of view of continuum physics and actually look at the equations that we have written as conservation of mass and conservation of momentum for every fluid element. So let me give you an example. So here is the fluid element. And here is the normal to the fluid, I mean to the boundary of the fluid element. Of course, the balance of mass is telling you that the amount of fluid that you have inside omega is constant. Okay, so if this is constant, it means the amount of particles which are leaving and entering the interface, they have to be the same. So this is just equal to the fact that the boundary integral of v dot nu is equal to 0. The flux of the fluid is equal to 0. Well, but of course, if you integrate this by parts, you get divergence of v equal to 0. And then if the integral of the divergence of v has to be equal to 0 for every fluid element, that is like saying the divergence of v has to vanish everywhere. Okay? This, if you can integrate by parts. But if you have, for instance, a continuous function v, which is solving this equation for every fluid element, that is actually a passable definition for what a less regular but divergence-free vector field is. And you can do something similar even for the balance of momentum. So you can write down the balance of momentum in this way. So one way to think about weak solutions is just to say, okay, I have a pair Vp in which I can make actually sense of these integrals, for instance, because V and P are continuous, for every fluid element omega which is smooth enough, so which is decent. And then for me, a weak solution is just a pair Vp which is solving these balance equations for every possible fluid elements, right? So that's a passable definition, and in fact, that's what books in continuum mechanics are doing for deriving the equations often. Okay, all these notions of weak solutions, they're all equivalent. Okay, so now why should we care actually about weak solutions? So, so let us go back to the Euler equations and let us add some small viscosity. So let us turn them into Navier-Stokes, but with a small viscous constant epsilon, which is of course assumed to be positive. Now, let us rewrite down the balance equation for the energy. Of course, once I scalar multiply this term, I get, again, the total derivative of the kinetic energy, and this time the typo is important. So here, of course, I have to divide by 2, because this time the right-hand side is non-zero. So here, I should divide by 2. Of course, now, the term over here, when I scalar multiply by V, is not anymore vanishing. I mean, before I had 0 times V, so equal to 0. So if I integrate it by parts, then I get this thing over here. And of course, that's what we are expecting. So if we have a dissipative term over here, we are expecting that the kinetic energy is dissipated by the friction, right? So I will name this actually Q of T, and see that there is an epsilon in front of it. Okay, so now, of course, what you would say is if I have a sequence of smooth solutions, which is converging to a smooth solutions of the Euler equations, this kinetic, I mean, this Dirichlet integral over here is under control. Epsilon is going to 0, so that term goes to 0. But on the other hand, if you open a book in the theory of turbulence, you see that the Kolmogorov's theory of fully developed turbulence, what is called K41 theory, predicts, in fact, that for most solutions, whatever you understand for most solutions, because there is no clear, that I know of at least, there is not yet a clear way of putting a probability measure on the space of solutions, which actually in 3 dimensions we don't even know whether they are unique or not. But assuming you can do something like that, for most solutions you actually expect that this quantity over here is independent of epsilon. And it should actually be related to the kinetic energy by this law over here, okay, where beta is just a constant. This, of course, provided you have some assumptions on the flow, for instance, that the macroscopic scale of the flow is fixed, say 1. Okay? So now, of course, if you're imagining that something like this holds true, if it is happening for most solutions, I should find a sequence of solutions to Navier-Stokes in which the viscosity is going down to 0, but this guy stays bounded, in spite of the fact that you have an epsilon multiplying it. Okay? So now, that's what you're expecting, therefore. So you're expecting the existence of a sequence of solutions V epsilon k to the Navier-Stokes equations with the viscosity which is going down to 0, epsilon k goes to 0, the energy which is bounded, and the dissipation which is bounded from below, independent of epsilon k. Now, I don't know of any way, or I don't know of any result which is actually showing this for just one sequence, although the theory predicts it's typical. Okay, so actually, now coming to Lars Onsager, a famous theoretical physicist of the last century. So in a famous paper published on 1949, proudly on Nuovo Cimento, an Italian journal, and this was, I think, after a big conference on statistical physics. So he actually rederived Kolmogorov's theory independently, but he also explored the possibility of simply saying, okay, so if there is a behavior like this when epsilon is going down to 0, then why don't we put directly epsilon equal to 0? And when we put directly epsilon equal to 0, we try to develop a theory of ideal turbulence, and we should expect the existence of weak solutions to the Euler equations which dissipate the kinetic energy. Why weak solutions? Because the classical solutions don't dissipate the kinetic energy. Okay, so actually in his paper he advanced a remarkable conjecture. So remarkable for being so precise in mathematical terms, and remarkable for being true then in the end. So the subject of this talk is actually that the conjecture is true. It has been proven just last year, actually. So, and it's a very complicated and difficult proof. Okay, so the conjecture was the following. So say that you have a periodic weak solution of the Euler equations and assume that it satisfies a Hölder condition, a Hölder continuity. So we saw that if it is, we saw that if the solution is C1, then the energy is conserved. I was actually assuming C1 just to make the computations nice, but if I had assumed Lipschitz, the computation would have been the same actually. Even with Lipschitz regularity, you would have concluded conservation of the energy. So let us say that you put Hölder, and then depending on how large is this Hölder constant, there is a sharp difference between weak solutions. So if this Hölder constant is above 1/3, then the total kinetic energy of V has actually to be constant. And again, there is the factor 1/2 missing. But the interesting part, well, that of course is also very interesting, we will see later, but the other part which is kind of astonishing for a physicist in 1949 is that he conjectures if you have alpha below 1/3, then there should be weak solutions whose total kinetic energy is not constant. Okay? And this 1/3 is not just a random exponent. So this 1/3 is connected to the 3/2 that you saw in the slides on Kolmogorov theory. Okay? So this 1/3 is an exponent with a physical significance. Okay, so actually, one of the things that I always like to do when I am in the audience is to challenge the speaker. So especially often when you're listening to a talk in mathematics and the mathematician is talking about what physicists have said. Usually the mathematician is claiming something. If you actually open the paper written by the physicist, you find something else. I mean, there is a translation procedure. And in translation procedures, something is often lost. So you could really ask me, so wait a second. So Onsager was a theoretical physicist. Actually, he got a Nobel Prize in chemistry. And in 1949, could he really be stating such a conjecture in the language of weak solutions as we are doing now? Well, it actually happens that he really does so. So first of all, the Hölder condition is exactly what I've written down. You can check it in the paper. Then the only point is, what does he mean by a weak solution? And it's very precise. So in fact, he states first in one paragraph, he first states the conjecture, and then below he says, now I should tell you what I mean by weak solution, because of course, since I cannot differentiate V, what does it mean to be a solution to the equation? And it's interesting because it just takes a very rigorous definition. It takes exactly the Fourier series expansion definition. So in the previous paper, he has derived the infinite system of ODEs for the Fourier coefficients. And what he says in his definition of weak solution, you just assume the minimal condition which guarantees that this system is well defined. So the minimal condition which guarantees that the nonlinear term gives you a series which is summable. Okay? So it's, in the end, it's our generalized weak solution because you can prove that between the Fourier series definition and the distributional definition there is perfect identity. Okay. The other thing is that actually in his paper he is not, I mean, of course he's saying the energy is not conserved, but he's implicitly assuming the existence of weak solutions which dissipate the kinetic energy for the Euler equations, right? Because he's coming from Navier-Stokes, where he has a certain dissipation. He's getting epsilon back to zero. I mean, is letting epsilon go to zero. The final solution that you should achieve of the Euler equation should have actually the energy which goes down, okay? Now, on the other hand, if you only look at the Euler equations, you can actually make a change of variables and transform positive time in negative times. So once you have solutions which dissipate the kinetic energy, you also have solutions which increase the kinetic energy. Whether these solutions, you like them or not, when you actually reverse time, should come from some vanishing viscosity approximation or from some other conditions that you put ad hoc. But you cannot read it from the equations once you have non-conservation of energy. Okay, so the first part of the conjecture, that is, that for exponents larger than 1/3, the energy is conserved, was proved by Konstantin A and Titi in 1993. Actually, at the same time, a little earlier than Konstantin A and Titi, Inc also got to the exponent 1/3. Let's say morally, because he didn't actually prove the precise statement of Onsager. So he proved energy conservation for a scale of spaces which has 1/3 of a derivative, like the Hölder spaces, but not for the Hölder spaces. I mean, for slightly different functional spaces which have kind of similar flavor. Okay, so now what about actually the other part? So can you construct solutions which dissipate or do not conserve the kinetic energy? So the first thing I know of, so the first rigorous proof that there is a weak solution which does not conserve the kinetic energy is a famous theorem by Scheffer in 1993. So he proved it in 2 dimensions, and he proved it on the whole 2-dimensional space, not in the periodic setting. Anyway, he proved that there are compactly supported non-zero weak solutions. So compactly supported ancient solution, compactly supported in time. So of course they are violating the energy conservation, because if back in time they are equal to 0, at a certain point the energy conservation should tell you that they are always equal to 0. So in 1998, Sascha Schnirelmann gave a different proof. And so as I said, obviously these solutions do not preserve the kinetic energy, but you could ask whether there are solutions which dissipate the kinetic energy. So from now on, when I have solutions of the Euler equations which dissipate the kinetic energy, I will call this anomalous dissipation, as it is actually done in the literature. And he did prove in 2000, but in 3 space dimensions, that actually it is possible to construct weak solutions of the Euler equations for which the energy really goes down. And of course, these solutions cannot start from 0 now. Okay, so in 2007, with László Székelyhidi, we proved that there are compactly supported non-trivial bounded weak solutions in any space dimension. And not only that, so our construction gives you solutions with a nice energy profile in time. So the construction of Scheffer might have given you a solution with an energy profile which is very rough. Our solutions, they might have energy, I mean, you might construct them in such a way that they have energy which is going up and then is going down. So if you only look at our solution from a certain point on, our solutions are also truly dissipative solutions. And they are bounded, and they exist in any space dimension. And in fact, you can do much worse. In a sense, you can construct weak solutions which behave as badly as possible. So you could ask, okay, so these weak solutions, they violate, for instance, the uniqueness of the solutions for the Cauchy problem, but if you complement them with some additional conditions like conservation of energy or dissipation of energy, local dissipation of energy, whatever, can you restore the uniqueness? And so far, for all things which have been proposed in the literature, the uniqueness of weak solutions for the Cauchy problem can actually be given a counterexample by the methods of our proof of this theorem. And you don't need initial data which are too discontinuous. Actually, mild discontinuities in the initial data trigger already this non-uniqueness phenomena for weak solutions. So similar conclusions hold for a lot of other equations, and there are actually a few people that have picked up our methods and used them in other contexts. I mean, here you see a list of them, and it's not an exhaustive list. I mean, at least it was an exhaustive list up to a couple of years ago, maybe, but now there are even more people. Okay, so now actually what is interesting of our 2007 paper is that ultimately it led us to a train of ideas which then 1 year ago led to the proof of Onsager's conjecture. So that's the topic of the talk. So what did we do in 2007? So Scheffer and Schnirelmann constructions, they look like kind of isolated in the literature. So what we actually realized is that, for instance, Scheffer's theorem, you can prove it with a method which in another field of mathematics is essentially classical, and the other field of mathematics is the theory of differential inclusions. So what is a differential inclusion? So a differential inclusion is a problem in which you're looking at maps and you assume that the differential of the maps belong to a certain given set, K. So the way we were thinking of the other equations is, instead of having vector fields U and prescribing a set for the differential of U, a constrained set, in the Euler equations you're looking at divergence-free fields, and you are prescribing that these divergence-free fields take value in a particular algebraic set. So there is a similarity between the two problems. Now, when you are considering problems in differential inclusions like here, actually, usually you don't consider C1 solutions, because C1 solutions are very rigid. For most examples which are interesting, you consider Lipschitz solutions. So Lipschitz solutions of problems in differential inclusions, they are kind of cousins of L infinity solutions to the Euler equations. So let me give you an example. So a toy example is the iconal equation. So you assume that the modulus of the gradient of a given function is equal to 1. And then maybe you add some boundary conditions. So now what I want to show you is an iteration mechanism which is producing a unreasonable solution of the iconal equation. Okay? So, and you have to think of this iteration mechanism as a toy example for the iteration mechanism which is producing these bad solutions of the Euler equations. So let me tell you that I start with a function which has modulus of the gradient less than 1, strictly less than 1. And now I want to set up an iteration scheme which is finishing at the end in the limit into a true solution of the iconal equation. So this iteration scheme is producing from a smooth phi 0, a smooth phi 1, and so on. And along the iteration, I'm always below in modulus with all the gradients. I'm always below 1. But in an average sense, if I look at the integral distance to be a solution of the iconal equation, so if I look at this integral, it actually decreases step by step by a non-trivial factor beta. So beta is less than 1, right? So 1 minus beta is the factor by which this integral decreases. Of course, if I have such an iteration mechanism, this integral, right, along the sequence is decaying exponential, so it's going to 0. And if I could prove that phi k is converging strongly to some limiting function phi, the limiting function phi will have modulus of the gradient equal to 1 almost everywhere, because it's just passing the limit in the integral. So first of all, let me tell you that, of course, proving strong convergence for phi k is not easy, but let me give you an idea on how you set up the iteration. So what I'm going to do is I'm passing from one function of the iteration to the next one, ignoring what happened before. So at each step, I'm just taking the function that I got before and I'm upgrading it to a kind of sub-solution of the iconal equation, which gets closer to be a solution. So phi k is actually smooth. So if I look at a small dot over here, at a small circle, and I magnify, the gradient of phi will be almost constant, right? So the gradient of phi is continuous, so it's not varying much on this circle. If I make an homotopy, I get a function over here which is almost linear. Now, if I have a function which is almost linear, let's say the slope will look like this, right? The cross-section of the slope. Now, the problem is that this slope is not equal to 1. Now, although this slope is not equal to 1, I can zigzag close to this slope and make all the slopes of the zigzag equal to 1. But then I want actually a smooth perturbation, so I can just make my slope almost equal to 1 and then make a sharp transition. So this modification, this perturbation of my function will have, in an integral sense, the modulus much closer to 1, while staying always below 1. Okay, so if you look in formulas, what I'm doing, I'm taking the function phi x, and I'm adding a wavy perturbation. So the wavy perturbation looks like this. It's 1 over lambda, a periodic function of lambda x. And the larger I choose this lambda, the more periods I have in my, the smaller period I have in my oscillation, and the more oscillations I have. Now, one of the problems is that if I am here, right, my slope is in this way, and then I have to make a wavy perturbation in this way. But if I am on some other region, the slope is totally different, and the wavy perturbation has to be totally different. So I have to make my construction compactly supported, essentially. And what I'm doing, I'm multiplying my perturbation by a cutoff function c, which is compactly supported in my small region. Okay? Well, once I do that, of course, it's a little bit tricky because a cutoff function has very high gradients, right? So, but if you make a simple computation, you see that the gradient of my perturb function is the gradient of the old function. Then there is when the derivative falls on the perturbation p and not on the cutoff, and this is improving my slope to 1. And then there is when the gradient falls on the cutoff, and this is a kind of error term. Now, the error term has a 1 over lambda term. And if I take lambda very, very large, this error term actually can be considered as a small error. Okay? So now I do this by taking lambda very large in such a way that the improvement pushing the slope to 1 improves my integral in a substantial way. And the error term is not destroying my improvement. At the same time, I will take care that the modulus of the gradient is less than 1. And this I just do it by the improvement not getting too close to 1, and of course the error not destroying this estimate. Okay, so now I have improved my solution on some small circle, but of course I can just make a covering of a substantial portion of my domain omega, and I can improve my solution to have slope equal, close to 1 on all of these small disks in my covering of a substantial portion of omega. Okay, so this is just by saying that I cannot increase the integral everywhere, but of course I can increase the integral on a non-trivial portion of omega. On a constant portion of omega, right? So this is just a simple covering argument. Okay, so now what about convergence? Well, obviously phi k is converging to phi uniformly, right? So I have a uniform bound on the modulus of the gradient, so I am equi-Lipschitz. So Arzela and Ascoli proved long ago that then you have a subsequence which is converging uniformly, okay? But what about strong convergence of the gradients? That's a different business. And actually it looks dangerous, right? So because the typical counterexamples to strong convergence as opposed to weak convergence are exactly adding oscillations. So actually this method is giving you that gradient of phi k does converge strongly in L1 to gradient of phi. And the upshot is that the oscillations that you are adding, they are always at a different scale. So at each step of the iteration, you are adding, you see this lambda is growing very, very, very fast. So it's like looking at a lacunary Fourier series. And lacunary Fourier series, they have much better convergence properties than usual Fourier series. Well, there are two ways actually of proving that gradient of phi k are converging to gradient of phi. At least there are two tools available in the literature. One is called Baire category argument, and it was pioneered by Cellina on one-dimensional problems, later on taken by Bressan and collaborators, and then Da Corogna and Marcellini were the first to use them in a higher dimensional context. And probably the most elegant implementation of this method is in the habilitation thesis of Bern-Kirchheim through Banach-Mazur game. But there's another method to do the same, and it's called Lipschitz convex integration. This was actually introduced by Müller and Schwerak in 1999. Now, this Lipschitz convex integration is especially relevant for us for the following reason. So what Müller and Schwerak actually realized at the time is that, okay, so the upshot of all these crazy constructions is that, so in the Euler equations, in differential inclusions, is that you are producing a solution with a very unusual iteration mechanism in which you're piling up finer and finer oscillations at each step. And the oscillations become faster and faster, so fast that when you actually want to control higher regularity, you essentially are not able, because if you want to control higher regularity and you have to compute higher derivatives, the oscillations now, the lambdas get multiplying your series, and the series is blowing up, okay? So Müller and Schwerak actually realized that what people were doing in the literature of differential inclusions in the 80s and 90s, and in 2000 also, had already been done in a different framework in geometry. And in particular, this Lipschitz convex integration that they introduced is a variant of what is called Gromov's convex integration, which is a tool to prove H-principal results in geometry. Now, I'm not going to tell you what is an H-principal result. I'm just going to give you an example. So there is an old tradition of counterintuitive constructions in differential geometry, and perhaps the very first is the so-called Nash-Kuiper theorem. So the Nash-Kuiper theorem says the following. So take a Riemannian manifold, so Mg. An isometry in Rn of this Riemannian manifold is a map U from my manifold into Rn, which is preserving the length of the curves. Okay, so now in what follows in this talk, we will always be talking about C1 maps, which are also embeddings. So they will be called isometric embeddings. So I'm not stating the Nash-Kuiper theorem, but I'm stating a corollary. So consider the standard sphere or the flat square. So what you can do is, for any given epsilon bigger than 0, you can actually find C1 isometric embeddings of these manifolds in a Euclidean three-dimensional ball of radius epsilon. So this might not seem particularly surprising, but let me give you a practical demonstration of this. So this is in fact very surprising. So first of all, because if you try to replace in the theorem C1 with C2, then it's false. And it's an old result in geometry. I mean, Von Vossen and Herglotz already proved it before the Second World War. So if you're trying to embed the standard sphere with a C2 isometric embedding in R3, then you get the standard sphere, meaning you get the boundary of a ball of radius 1. You cannot compress your manifold in anything shorter than a ball of radius 1, okay? But actually, you can think about it with, I mean, it's easier to visualize it with a flat manifold. So this is a flat manifold, and this is an isometric embedding. So an isometric embedding means I'm not actually changing the length of the curves. I mean, if I tear, of course, the paper, then I'm changing the length of curves. Otherwise, I'm not. And I cannot stretch it, right? So this is not elastic. So I cannot make curves longer. Now, of course, a cylinder is a perfectly good bending of a flat manifold. So I can do this, right? And I can make it, I can make it short in this direction, right? But if I try to put it in a ball of radius epsilon, somehow I have to make it short also in this other direction. And it doesn't seem possible. See, I mean, whatever I do, it seems I'm creating singularities. So now this is not anymore a C1 isometric embedding because I'm creating a corner. So it's a Lipschitz isometric embedding. So it's very, very surprising that you can do that. And it was a huge surprise for geometers at the time. Now, what does actually an isometric embedding have to do with differential inclusions? And with this story? Well, the isometric embedding is a differential inclusion. So you can write a system of partial differential equations for the isometric embedding. And the system looks like this. So the transpose of du times du is equal to this tensor G. It's actually not too far from this iconal equation, right? I mean, the iconal equation is really a baby model for this. Because you see you have essentially a quadratic term in the differential equal to something fixed. Okay, so when we actually were looking at this, well, first of all, we had this realization that, okay, so we have a proof of the Scheffer-Schnirelmann result, which looks like what people in differential inclusions do, which looks like what Nash has done back in the 50s. But then we also saw that there was something interesting in there also. So I told you C1 isometric embeddings have this crazy construction of Nash and Kuiper, but C2 isometric embeddings have the classical rigidity behavior that you would expect from Von Vossen and Herglotz. So you could ask the question, what happens if I put a C1 alpha regularity and I just vary alpha between 0 and 1, right? So when I reach 0, I am in a Nash-Kuiper situation. When I actually raise it to 1, I am essentially C2, and I am in the rigidity situation. So is there a threshold in between? And we were not the first, actually, to think about that. Borisov, a Russian mathematician, actually came up with this problem back in the 50s. And what he proved is that the Nash-Kuiper theorem is valid for C1 alpha isometric embeddings when alpha is small enough. And the best exponent for two-dimensional disks is actually 1/5. This is a recent paper by László, myself, and a student, Dominik Inauen. On the other hand, the rigidity theorem of Von Vossen is valid for C1 alpha isometric embeddings when alpha is large enough. And the threshold, which is currently known, is 2/3. So here, unfortunately, there is no physics guiding us to a guess of what the threshold should be. But there are some indications in favor of 1/2. And actually, this is now a conjecture of Gromov that 1/2 distinguishes between rigidity behavior and flexibility for the isometric embeddings. OK, so let us go back actually to the Euler equation. So in a sense, the theorem of Nash-Kuiper is much more general. There is something which is called an H principle. And the H principle tells you something like this. If you give me a short map, so a map which is decreasing length, I can uniformly approximate it with C1 isometric embeddings, so with exact solutions. You see, it looks a little bit like what we were doing with the iconal equation. We started with a subsolution, and we constructed a true solution as a perturbation of this subsolution. And when we are adding these perturbations, we always stay nearby, right, in the C0 norm. So this is what Gromov actually calls an H principle. And what we proved in 2007 is that there is a statement like this for weak solutions of the Euler equations. So there is a way of defining a subsolution of the Euler equations. And nearby, in a weaker topology than what is the regularity of the solutions, I'm finding a lot of weak solutions. So we came up with the crazy idea that maybe this conjecture of Onsager can be understood as a type of H principle for the Euler equations. Of course, now here there's a big caveat. So in analysis, people usually work in the L infinity space. And so our result was for L infinity solutions. Whereas in geometry, in the words of Gromov, no self-respecting geometer would actually work in these type of spaces. They would work in C0 type spaces. Okay, so in 2011, we proved that our L infinity construction, well, not really our L infinity construction, because in the end, the proof looks much different. But we proved that a kind of H principle can actually be carried on in the framework of continuous solution. And this is the proof, the theorem that we proved. So you give us the energy profile that you want, and we can produce continuous weak solutions which have that energy profile. Particularly if the energy is going down, we can produce continuous weak solutions with dissipating energy. Okay, so this is actually the first time that in the analysis of PDEs you use this type of arguments in the C0 category, which is instead customary in differential geometry. It also actually answers the question of Gromov because it is a convex integration construction in which we invert or we integrate more complicated elliptic operators rather than the usual constructions which integrate kind of easy one-dimensional operators. Anyway, slightly after, since we had our experience with the isometric embedding problem, we could actually upgrade our construction to a Hölder exponent, so which is not yet the 1/3, but it's also not too far. I mean, it's this 1/10. And as it happened for our previous theorem, somehow the people actually, several people discovered that you can do a lot with these methods. So you can prove non-uniqueness, you can use it in 2D, and you can even actually deal with different equations. You don't have to be necessarily the Euler equation. So the method is much more flexible than we thought at the beginning. So now, how does this method work? So it's an iteration mechanism, and you produce a sequence of smooth solutions of the Euler equations, which are approximate solutions. So instead of having 0 right-hand side, you measure the distance to be a solution of the Euler equation by this tensor. So this is a symmetric 3×3 trace-free tensor. And what is happening is that along the iteration, this tensor is going uniformly to 0. So your iteration mechanism is producing a sequence of solutions to these approximate Euler equations, where the right-hand side is going to 0, and VQ is Cauchy, for instance, in C0, and so it's converging to a weak solution. So how do we do this? So the key idea is similar to the toy problem. So at each step, we correct VQ, PQ by adding a lot of oscillations, so highly oscillatory perturbations. Now, it's not as easy as in the toy problem, though. So the high oscillations are stationary solutions of the Euler equations with slowly varying coefficients. So they are not something that you can really write down explicitly. You have to solve the partial differential equation to produce them. And there's something important. So these are static perturbations, and the Euler equations are evolutionary. So you actually have to transport the oscillations along the flow of the previous fluid velocity. So in a sense, what you're doing is you're like of making a quasi-stationary perturbations of the VQ, because the oscillations are much faster than the advection of the fluid velocity for the VQ of the previous iteration. Okay, so now let me step back in the middle, because often I get questioned on what is the meaning of these weak solutions. And I want just to make the point that I might state all the theorems with weak solutions because they're in the end elegant to state and very short and compact. but I can actually state the theorems with no reference to weak solutions whatsoever, and always use C infinity functions. Because you see, what's happening is that if I go back to my approximate solutions, I'm really producing sequence of smooth solutions to this system with this tensor, which is a kind of stress tensor, which is going to 0. So if you look at the energy balance for our solutions, the energy balance looks like this. So here you have the usual blue term, and then you have the red term, which is a kind of dissipation. So if you write down the dissipation of the total kinetic energy, you get this identity. So the total kinetic energy gets dissipated by this term. Now what happens is that although our circle Q is going to 0, and VQ is converging to V, so it's kind of under control, this red term is not vanishing in the limit. And in the limit, I get a solution of the Euler equation for which the kinetic energy is dissipated. So now, of course, you could say, well, how far are we from what should be the true picture of a turbulent fluid? So the true picture of a turbulent fluid, we would actually get it if we were able to solve Navier-Stokes. So what I would like to do is therefore to replace the stress energy, the stress tensor R circle Q by epsilon Q times the derivative of VQ, where epsilon Q is a small viscosity coefficient, which I can guess actually from the construction. And I told you that this R circle Q is symmetric and trace free. Well, this R circle Q, ideally, I would like it to get equal to the symmetric part of the derivative of the velocity, which is trace free and symmetric. That actually amounts to solving the Navier-Stokes equations. If I could replace R circle Q by epsilon Q dVQ plus dVQT, then I would have an answer to this question that I posed at the beginning, a sequence of Navier-Stokes, of solutions of the Navier-Stokes equations with viscosity going to 0, and which is actually displaying dissipation. And the reason, you might wonder, right, because I have this term in this equation, but since VQ is divergence free, when I take this divergence, actually this term drops out, and here I just have the Laplacian. So that's all I want to do. And actually, it's remarkable because in our construction, this R circle Q can be written in this form for a vector potential. And the vector potential has a lot of structural conditions which are similar to the velocity. For instance, it's divergence free. It has the same estimates. It kind of has the same Fourier energy spectrum. So there are a lot of things which are similar to VQ. But of course, it's not VQ. Okay? So the upshot of these slides is that if you go back somehow, I could completely erase the name weak solutions from all my theorems, and I could just say that I produce a sequence of smooth solutions to a perturbed Euler system, which is not, unfortunately, Navier-Stokes. Otherwise, it would be a fantastic theorem. But in some sense, it can be thought as a progress to producing a sequence of solutions to Navier-Stokes, which is displaying this anomalous dissipation, because you have a lot of structural conditions which are similar. And all the thing I would like to do is to actually replace my stress tensor R circle Q by this dVQ plus dVQ transpose. Okay, and if I were able to do that, I would have a solutions of Navier-Stokes with vanishing viscosity, with bounded velocity. Actually, if I were in the conjecture of Onsager, I would have it with a uniform control on the Hölder norm, and I would have anomalous dissipation, meaning a bound from below for the total dissipation of the kinetic energy. Okay, so now back to the Euler equations and the iteration. So I'm just repeating a slide which I had before, because I want to go back to it in a few seconds. So I'm producing an iteration in which I solve this with smooth solutions, and the right-hand side is going down to 0. And just remember the key ideas. We are correcting by adding highly oscillatory perturbations. The high oscillations are stationary solutions of the Euler equations. They are Beltrami flows. And the static perturbations are advected by the velocity VQ that we are trying to modify. Okay? So the first improvement to our 1/10 exponent actually came in the PhD thesis of Phil Isett, right after our paper, in fact. And he was able to show that there are, for alpha less than 1/5, there are non-trivial compactly supported weak solutions with this Hölder regularity. Now, of course, non-trivial compactly supported weak solutions means they're not conserving the energy, but it's not clear whether they actually are dissipating the energy somewhere, right? So because a Hölder function might have a behavior like Brownian motion, so the energy profile might actually be doing this. So what are the key ideas? Well, it has a better way of transporting the oscillations. So because actually what happens is that you cannot truly transport the oscillations along the previous VQ. The reason is that VQ, although it's regular, it has very bad estimates. So if I make a transport through the flow of VQ for a very long time, actually the transport might behave in a very chaotic way. So I have a way, one has to find a way of approximating the transport equation efficiently. And it has a better way of approximating the transport equation efficiently and more careful estimates. So one particularly important thing which I will stress in a couple of seconds is that, so if you remember my constructions of the solutions of the iconal equation, I had these dots, right, in which I'm making the perturbation. I was doing an L infinity construction, so I was making my perturbations on the dots. And then I was leaving the solution unchanged outside of the dots. I can't do that. I have to modify my solution everywhere, because I have to stay uniformly close to it. So I cannot allow to make a perturbation somewhere and to be unperturbed somewhere else. So this means actually that where I was making a simple covering argument and making my modifications compactly supported, in this business, I have to use a partition of unity. And that creates a hell of a lot of problems, because where the different support functions for the partition of unity are conflicting, I get a lot of bad error terms. So one of the key ideas of Phil is that in our original paper, we were doing a partition of unity in space and time. It's actually able to get away with a partition of unity only in time. So with much less overlapping problems. Okay, so now with Buckmaster and László, so Buckmaster is a former PhD student of László, so we realized actually that you can make, you can use Phil ideas and make the proof, first of all, shorter than what he had, and then secondly, you can actually prescribe the kinetic energy. So you can get the anomalous dissipation, whereas he was getting non-trivial compactly supported solutions. But also, Tristan noticed that you can actually get almost to this threshold 1/3. In fact, if you modify this partition of unity in time suitably and you make a lot of work, you could actually prove that your solution is 1/5 Hölder globally, but at most times it's almost 1/3. So this led essentially to the first time that the threshold 1/3 was reached. So in a paper with Tristan and László, we actually proved the existence of non-trivial compactly supported solution in this space, L1 in time and Hölder 1/3 in space. So what does this mean? It means that if I take the modulus of continuity of V in space at each time t, so this is Hölder, but the constant that I have in front, the Hölder norm, is not uniformly bounded in t. It's only an integrable function. Nonetheless, the 1/3 threshold is there. So here we have a solution with 1/3 of a derivative, so Onsager critical, which is not conserving the kinetic energy. Okay, so the conjecture of Onsager is just then to replace this L1 function with an L infinity function. Now, actually what happened is that this has been done last year, but the proof is not building on this theorem. It's building, of course, on the previous methods, but it's building on two important ideas which actually appeared in 2016. So first of all, Saradaneri and László replaced the local perturbations, so the local oscillations, by a different set of solutions, of stationary solutions of the Euler equations. So they replaced Beltrami flow with another family of solutions of the Euler equations. They're supported in thin tubes. They call them Mikado flows. And they couldn't improve actually this 1/5 minus epsilon threshold that was true at the time, but they could prove what is the first kind of satisfactory H-principle statement for these problems. So you remember these H-principle statements tell you if you have a suitable notion of subsolution nearby, you find a weak solution. So ultimately, the existence of, the possibility of achieving any energy profile, which was our previous theorem, is just a corollary of this H-principle. So the existence of solutions which dissipate the energy is just a corollary of this H-principle, which is telling you that there are plenty of solutions in low regularity. Now, one thing which is very nice to notice is that their construction is not possible in dimension 2. So far, whatever I told you is all possible also in dimension 2, not only in dimension 3. But this theorem in dimension 3, it's only possible in dimension 3 and not in dimension 2. And the reason is geometrically very simple. So at a certain point, they are using the geometric fact that, unlike in 2D, you have plenty of lines in 3D which are not parallel and which do not meet. In 2D, if you have two non-parallel lines, they have to meet somewhere. And in 2D, for this reason, you cannot carry on their proof. Okay, then finally, Phil Isett, in August 2016, so last year, he actually proved then that there are non-trivial compactly supported C1/3 minus epsilon solutions. So this time, the Hölder norm is uniformly controlled in time. Okay, and what is he doing? Well, okay, this is a typo actually. He's in the periodic torus, not in OLR3. So what is he doing? So he's using the Daneri-Székelyhidi-Mikhailov law, and then is able to remove this partition of unity in time, which I told you was creating a lot of problems. How does he do that? He does it by kind of, in a first step, making the error compactly supported in small separate stripes of time. Then he can implement actually the modification in each separate stripe of time. And how does he do that? Well, in the intermediate stripes, he solves the Euler equation. He plugs in an exact solution of the Euler equation. Now, of course, when can you do that? Well, you can do that, you have smooth solutions, so you can do that as long as the time is short enough, right? So because the initial data has a certain norm, if the time is too long, then you don't know that there exists a solution of the Euler equation. And what is actually very nice is that the size of the interval, which is related to the regularity of VQ along the iteration, is exactly compatible with the construction. So the size of the interval which gives you well-posedness of the Euler equation is exactly compatible with the best estimates which lead you to the solution of the Onsager conjecture. And actually this is something that it was noticed previously in the previous papers. And that's a kind of remarkable, well, probably it's not a coincidence, but at least it's a remarkable lucky thing for which we don't have a deep explanation at the moment. Okay, so final touch. So it is actually possible to improve his proof and show that the same H principle of Sarah and László actually holds for this C1/3 minus epsilon solution. Of course, epsilon has to be positive, so we don't know what happens at the critical exponent. And as a corollary, so previously he had compactly supported solutions over here. Now, by improving his proof, you can actually show the existence of anomalous dissipation for this threshold. So truly, C1/3 minus epsilon solutions whose energy is just going down. Okay, and well, that's what I would call finally the Onsager theorem by summing up all the results, and thank you for your attention.
So, are there questions?
So, is this anomalous dissipation? Is this anomalous dissipation of the form epsilon d square for some velocity field, for some velocity perturbation, as you indicated before?
No. So what it is, it's okay. So along the iteration, it looks like this. it will look like this. And I don't know that this ZQ is VQ. So this ZQ will have a lot of similarities. It's divergence free. It has a similar energy spectrum. It has similar estimates in terms of size and so on. And moreover, this integral is positive. So it has a sign, right? But I cannot show its VQ. Now, I don't know if I can write it as, maybe, I don't know if I can write it as the integral of the derivative of the square, I mean, of the square of the derivative of something which is meaningful. That I don't know. I can write it in this way, though.
Can I have one more question? At the beginning, you mentioned 3 possibilities of definitions of generalized solution, but you did not come to the last one somehow in the talk. So what would be? And also in that definition, you had to assume that V and pressure are continuous somehow to define the traces or to
Right.
So you first mentioned that these definitions are equivalent, but for first two you work in L2, but for others you work in continuous functions.
Yeah. So let's put it this way. If you give me a continuous function, all the definitions are equivalent, all of them. Mm-hmm. Now, if you change the regularity, of course, you have to give kind of meaning, for instance, to the integral over the boundary, right? I mean, for instance, if you pick up an L2 function, then I need a trace theorem. So for an L2 function, the trace is not defined for every omega, but it will be defined for almost every omega out of a Fubini argument. Mm-hmm. So if instead of asking the balance of mass and momentum for every omega, you ask it for, sufficiently large class of omega, and you plug in a measure theoretic setting, then you can really also go from distributional solution to solutions in the sense of local conservation of mass and momentum. Mm-hmm. But it's of course not as strong as computing for every omega. Mm-hmm. Yeah, so that equivalence is in a loose sense. You saw also in the Fourier series, I was assuming L2 at every time. Right? Mm-hmm. If you assume L2 of space and time, what will happen is that your series is summable for almost every time. So your ODE has an L2 right-hand side, which is in time. I mean, for each coefficient, you have an ODE which has an L2 right-hand side, L2 in time, which is still okay. So you can find the appropriate setting to make all the definitions kind of completely equivalent. But I wanted to avoid it, not to make things too complicated.
More questions? More questions? Okay, thank you.